let's talk about end behavior, horizontal asymptotes, limits at infinity. Those are all the same thing. So when we have limits at infinity, that is simply saying, well, how does our graph behave at negative infinity as x goes all the way to the left? Or how does our graph behave all the way to the right as x approaches positive infinity and gets very large? That is also called end behavior, or how the graph behaves on the ends, its left end and its right end. Now, this is a pre-calculus idea, but in calculus, we talk about it using limits. So we have this rational function here, and we'll just do this example first in a visual way. We can see that this is a rational function, and it actually has two discontinuities. We see that we have an infinite discontinuity here, a vertical asymptote at x equals 2, and we have this hole right here at x equals 3, so this is a rational function with two discontinuities, at least. Let's take a look at the left end behavior. This is how our graph behaves all the way to the left, and before we even do that, I'm going to call this function f of x, so we have a name for it. Our left end behavior we write as the limit as x approaches negative infinity. So the infinities are actually down here after the arrow. The limit as x approaches negative infinity of our function f of x. And let's see what happens. Well, we can see that as x gets smaller and smaller as we move left, what are our y values approaching? They are approaching the y value of 1. This is our horizontal asymptote y equals 1 right here. So the limit as x approaches negative infinity is 1. Then our right end behavior, we have sort of the same thought process here, but now to the right. So we write this as the limit as x approaches positive infinity. And now with infinity or positive infinity, we do not need to have a little plus symbol out in front here, but you can if you'd like. And we take a look at our function. What's our function doing as we go to the right as x gets larger and larger? We can clearly see that once again, our rational function is approaching the horizontal asymptote y equals 1 here. Now, it's approaching it from the top, whereas on the left side, we're approaching it from below, but it does not matter. We are approaching the y value of 1. So we would say that our right end behavior, or the limit as x approaches infinity of our function, is 1. Now, what if our function is not graphed for us and we can't do it in a visual way? Well, we have some algebraic rules that we can follow to figure out what our horizontal asymptote is or what our end behaviors are. In this video, we're going to talk about how to find the limits as x approaches negative and positive infinity of different types of functions. Those functions are going to be rational functions like here, what we just saw, and then also functions that involve square roots. Let's do some quick calculus. Let's take a look at this theorem here about limits at infinity or negative infinity. Here's the main part right here. When we have the limit as x approaches infinity of just any real number divided by x to the any positive rational number, so for instance 1 over x squared, that's just 0. Let's think about why that is. I'll give that example that I just said. We'll do that in yellow here off to the side. So if we have the limit as x gets very, very large of, like I said, 1 over x squared. Okay, let's see how that fits this theorem here. Well, first of all, c is any real number. I just picked 1. Then x to the second. So r right here. R, is it positive? Yep. Is it rational? Yep. Awesome. So the limit as x approaches infinity of 1 over x squared, for example. Well, this means x is getting very, 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 very big, right? So this is 1 divided by a huge number, a number that's getting very, very large. Now that large number is getting squared, so it's even bigger and bigger and bigger and bigger. Well, think about dividing 1 by 100, 1 by 1,000, 1 by 1,000,000. You're basically getting so small that you're approaching 0. And that is why this limit holds as x approaches positive infinity. Now that we've seen that main theorem for a rational function, let's take a look at 3 separate rational functions here and explore their limits as x approaches both infinity and negative infinity. We'll start with f of x. We see that in the denominator here of our rational function f of x, We have our degree is 2, our lead coefficient's 3, some of those kind of pre-calculus ideas before we get started. Well, I can see that since the degree is 2, my leading term here is 3x squared. What we're going to do is actually divide every single term in here by x squared. So let's actually rewrite this to look like the limit as x approaches infinity, and now I'm going to rewrite my rational functions. Instead of just writing f of x, I'm going to actually rewrite this and divide every single term by x squared. Here's what it's going to look like. So I've divided both the numerator and the denominator by x squared because that is the main part of our leading term here. Technically, we could have divided everything by 3x squared since that is the entire leading term, but it just kind of unnecessarily complicates things. And when we divide an entire expression up here by the same thing, we are just taking each term and dividing it by that thing. So I'm taking every single term and dividing it by x squared because that is what our leading term was in the denominator here. All right, so let's simplify it. So we can see that when we simplify this first term here, so I'll rewrite the limit. When we simplify this first term here, 2x over x squared, one of the x's cancels, so I simply just have 2 over x as my first term. This 5 over x squared is going to stay as is. Down in the denominator, that first term will simplify just to a 3, and this will simply just be 1 over x squared. Now, using the properties of limits, we're actually taking the limit as x approaches infinity of each of these terms separately. So let's think about that a little bit as we look at this. So when we have the limit as x approaches infinity of 2 over x, well, we just learned that when we have a real number up top and x to a positive rational number right here, which is 1, the limit as x approaches infinity of 2 over x is simply 0. This goes to 0 again if you think about it logically. 2 over something extremely, extremely large, 2 out of a million, 2 out of a trillion is basically nothing. So this approaches 0. Same exact reasoning with this term right here. So what I'm going to do, I'm using that theorem, and up top I have 0 plus 0 because I found each one of those limits as x approaches infinity separately. Now in the denominator, the first term is 3. The limit as x gets very large of 3 is just 3. There's no x here to affect anything, so it doesn't matter what x is approaching. This function is just the constant 3. So that's going to stay 3. And I'm going to use that same reasoning as up here. The limit as x approaches infinity of 1 over x squared, according to that theorem we just learned, is 0. Simplifying this, I get 0 over 3. That is 0. 0 over 3 is 0. So in this case, our limit as x approaches infinity of f of x is 0. So I've gone ahead and just rewritten sort of this step down here to find the limit as x approaches negative infinity. So I once again divided everything by x squared, which was our lead term, the main part of our lead term in the denominator. Just again, we're not dealing with the 3. It's unnecessary. And so it's now simplified, and really we're going to get the same thing. Here's the reasoning. With that theorem, we said so long as x to the r is defined when x is less than 0. So if x is a negative number, so long as x to the first down here, x squared, if all of those are still defined when x is negative, we still approach 0. So the limit as x goes to negative infinity for these 3 terms right here following that theorem are all approaching 0. So we end up with the same reasoning here. We have 0 plus 0 in the numerator, and then 3 plus 0 in the denominator. 0 over 3 is once again 0. If you graph this function, you will see that both the right end behavior and the left end behavior are 0. The graph approaches 0 at both ends. Next, let's take a look at h of x. Once again, the denominator is actually the same. The numerator just has a degree of 2 now instead of a degree of 1. So that's really the only difference between f of x and h of x. All right, so once again, we're going to divide everything by x squared. Let's do that. So I've divided all of my terms by x squared, again, because the lead term here in our denominator, that is the variable part of it. So I divided everything by x squared. Let's now simplify that in our next step. So here, once we've simplified everything, it looks a little bit different than our previous example. we can see here that in both of our leading terms, in the numerator and denominator, the x squareds cancel. We're left with 2 and 3 respectively. Here we have 5 over x squared and 1 over x squared. Well, properties of limits say let's take the limit of each term separately. Well, 2 and 3 are unaffected by whatever x is. They remain 2 and 3. Over here, 5 over x squared and 1 over x squared, as x gets very large according to our theorem for limits at infinity, both of these are going to go to 0. So when we simplify this with each term, we'll be left with 2 plus 0 over 3 plus 0, which is 2/3. So our right end behavior, our limit as x approaches positive infinity, as we're looking at this graph to the right, our function approaches the horizontal asymptote of 2/3, whereas up here in f of x, we approach the horizontal asymptote of 0. Now, as we approach negative infinity, all of these two right here, x squared and x squared, those are both defined when x is less than 0, and so following our theorem, this limit is exactly the same. Lastly, let's take a look at g of x. We're going to do the same steps. So after dividing everything by x squared once again, we come to sort of a different conclusion than what we've seen. We actually have an x here that's not in a denominator because x cubed divided by x squared, only x squareds cancel. So here's what we're left with after dividing every term by x squared and simplifying. Well, let's see what happens to each one of these terms as x gets very large. Our first term, we might be able to say that it goes to infinity. I mean, if we're saying the limit as x approaches infinity of 2 times x, well, as x gets very large, 2 times x is also getting extremely large. So we could essentially say that this is basically infinity. Then our next term, we've established that that's 0. The denominator we've also established will be 3. So we essentially have something kind of weird mathematically, which is infinity over 3. Which is still infinity because if we take a very large number, or idea, which infinity is, and divide it by 3, it's still infinity. Next, let's take a look at the limit as x approaches negative infinity. I have gone through the process that we've been going through multiple times, so I divided every single term by x squared. Now here, if we are approaching negative infinity in this case, we've already established that the 5 over x, those should both be squared, rather. So the 5 over x squared and the 1 over x squared are both going to approach 0. Now, in this case here, the 3 is still going to approach 3, but this 2 times x, when plugging in a very, very small number, we are going to get 2 times negative infinity. And so when we get that, we could write it as negative 2 times infinity, but I'm simply going to write it as just negative infinity, and then it'll be over 3, which using that same logic is negative infinity. Now I know we have learned that we do not let overall limits equal infinity and negative infinity. However, these are called infinite limits at infinity. In reality, our function is just skyrocketing in both directions. This is actually a really rough sketch of what our function looks like. Our right end behavior shoots off to positive infinity, right? That's the limit as x approaches positive infinity. Our left end behavior, the limit as x approaches negative infinity. So as we look left, our function is going down towards negative infinity. So normally we would just call this end behavior. And in this case, g of x does not have a horizontal asymptote. It is not bounded by any horizontal line. Now, did we have to do all of that calculus, all of that dividing, all of the limit properties for those 3 rational functions? No. We can simply see that when we have a rational function, we just compare the degree of the numerator to the degree of the denominator. This is actually something that we learned in pre-calculus, but it's good to sort of relate it to calculus. Again, horizontal asymptotes are the y value that our function approaches all the way to the left as x approaches negative infinity, and or all the way to the right as x approaches positive infinity. Well, in order to find that without doing all of that algebraic work that we just did, we can follow these rules. N represents the degree of the numerator, and m represents the degree of the denominator. Let's compare them. We have 3 options. Either n is less than m, they are equal, or n is larger. If n is less than m, which we've seen, such as like 1 over x squared, something like that, then our horizontal asymptote, and therefore our end behavior, is the x-axis. It's simply y equals 0. That's when we found in our previous example for f of x. Right up here was f of x in our previous example. The degree of the numerator is 1, the degree of the denominator is 2, n is less than m, therefore our horizontal asymptote, the limit as x approaches infinity, is 0. Now, what if n equals m? What if the degrees match? Well, this example was h of x, where we simply changed, the only thing we changed that was different was the degree of the numerator. So here, when the degrees are the same, here the degree of the numerator and the denominator are both 2. The horizontal asymptote, aka the limit as x approaches infinity, is simply the ratio of the leading coefficients, a over b. Well, our leading coefficients were 2 and 3. Therefore, our limit as x approaches infinity, our horizontal asymptote, was 2/3. Lastly, what if the degree of the numerator is greater than that of the denominator? That occurred in our final example, g of x here. The degree of our numerator is 3 and the degree of our denominator was 2. N was greater than m. There's actually no horizontal asymptote. This function increases without bound. It's not bounded by some horizontal line. It doesn't approach some horizontal line. Instead, this actually shot off to infinity. So we said that the limit did not exist and there was no horizontal asymptote. Now, in this case, if the degree of n is 1 greater than the degree of m, which is the case here, 3 is 1 more than 2, we actually have an oblique asymptote. And if you do graph this, you will see that that just means that the function sort of looks like a line when you zoom out. It looks like an oblique line. So these are the rules that we can use in order to figure out what the limit as x approaches infinity is, aka the horizontal asymptote, for a rational function. You simply compare the degree of the numerator to that of the denominator. Lastly, if a rational function does in fact have a horizontal asymptote, it always approaches the same asymptote from both the left and the right. So if, in this case, right here, like we saw before, this rational function right here has a horizontal asymptote of 2/3, and both the left and right end behavior is 2/3, meaning the limit as x approaches negative infinity and the limit as x approaches positive infinity would both be 2/3. Same for this one right here. Now we're going to explore another type of function where we might have different end behaviors, different limits as we approach negative and positive infinity. In our final example, we're going to look at functions that are not just the more traditional rational functions. In this case, we have a function with a square root in it. Now, this is a type of function that is going to have two different horizontal asymptotes, meaning the limit as we go to the right, so our right end behavior as we approach infinity, is going to be different than our left end behavior, our limit as x approaches negative infinity. So let's take a look at each one. Let's take a look at our first function here. We're going to use the same process in that we want to divide by basically the degree, right, that term that is in the denominator. Well, if we take a look down here, we see that we have 2x squared as our leading term. I'm not going to worry about the 2. We have x squared, but it's under a square root, so we essentially have the square root of x squared. That's just x. So I'll write that out. Here's sort of my thought process just now. I want to divide by the square root of x squared using that same general idea as before, but that's really better just known as x. Now, that only is the case because this is a positive x value. We'll see how it's different in part B. But let's divide by either the square root of x squared or simply x to each term. So again, I'm dividing every single term that I can by x, but I'm simply writing it in a way that makes more sense mathematically because of what we have here. So now, simplifying this even more, we can clearly see that that will be our numerator, and our denominator can be written as one giant square root. When we're dividing two terms here and they're both in a square root, we can write it as one giant square root. So I'm going to write that just like that. And then we can clearly see that we can divide each one of those individual terms in here, each by x squared. So I can write it just like this instead, as two separate fractions. Continuously simplifying this, we will have we will have the square root of 2 plus 1 over x squared in the denominator. Well, now I essentially want to apply the limit to each term here. So in the numerator, this is going to stay 3. This is going to go to 0. And down here, we'll have the square root of 2 plus 0. So let's rewrite that. So we will have 3 minus 0 once we evoke the limit, and then the square root of 2 plus 0. So this is 3 divided by the square root of 2. If you want to rationalize it, we'll have 3 root 2 over 2. And that is our limit as x approaches positive infinity. So our right end behavior, our function approaches 3 over root 2 or 3 root 2 over 2. Let's see the difference in part B as we look to the left. We once again want to divide by the square root of x squared. Now, square roots, as we know, always come out positive. If we take the square root of 9, we get 3. We don't automatically get negative 3, so come with me on this tangent here, off in my brain. If we have the square root of 9, we'll get 3. But if we put a negative symbol out in front, that is okay. It's not the square root of negative 9, it's negative 1 times the square root of 9. That is negative 3. Therein lies the difference. So if we look at this with x, if I have the square root of x squared, I get x, the positive version of x. But if I want negative x to come out, how do I need to write that? I need to put a negative symbol out in front. Well, in this case, our x's are automatically negative because we're approaching negative infinity. So in order to make sure that we are getting the correct x, we have to specify a negative out in front of the square root. So I'm dividing everything by x, which is what we did previously. I'm assuming that our x values are negative because they are right here. It's the limit as x goes to negative infinity. But down below, if I divide just by this, that's a positive output. I need to make sure that it's negative. Here's how we can write it off to the side. Because x is a negative number, x, that negative number, cannot simply be written as the square root of x squared. It's negative the square root of x squared. That's our thought process here. All right, as we keep simplifying, we will have the limit as x approaches negative infinity. Our numerator can be simplified to 3 minus 2 over x. Our denominator can be rewritten as negative 1 giant square root. Again, because this is a positive up top divided by a negative, so division rules say we'll get negative. We're dividing two square roots, so we can write it as 1 giant square root of that division. And then this really means that I'm dividing each term by x squared. So I can simply write it like this, and this is all under that square root. All under the square root down there. Well, further simplification will give us this. In the denominator, we'll have negative the square root. That first term's a 2. The second term is plus 1 over x squared. We're ready to invoke the limit. As we do that, in our numerator, 3 will stay a 3. This next term will be minus 0. Then in our denominator, we'll have the negative the square root of 2 plus 0. So we essentially have negative 3 over root 2, or negative 3 root 2 over 2. This type of function actually has two horizontal asymptotes. The horizontal asymptote on the right side of our function is 3 root 2 over 2. This is our right end behavior. Then the limit as we approach, as x approaches negative infinity, our left end behavior is negative 3 root 2 over 2.